Have you ever noticed how time feels like a river you're carried along by, always moving, never stopping, with a past behind you and a future just out of reach? That everyday feeling is strong. Clocks tick, seasons change, memories accumulate, and we have a steady sense of now. But when physicists look at the world through the lens of relativity and modern cosmology, that intuitive picture gets shaken. Instead of a flowing river, some equations and experiments point toward something more like a landscape, a four-dimensional block that contains past, present, and future all at once. To get into that idea, let's begin with a very simple thought experiment that Einstein used to explain a deep, unusual feature of his special theory of relativity. Imagine a long railroad car or train carriage moving along the tracks. From the middle of the car, two bolts of lightning strike the front and back at the same time, according to an observer sitting in the middle of the carriage. They see the flashes reaching them simultaneously. Now imagine a second observer standing on the embankment watching the train go by. From that outsider's perspective, the train is moving, and because of that motion, the light from one strike reaches them a little before the other. So while someone on the train says the bolts struck at the same time, someone on the embankment says they did not. Two honest observers, looking at the same events, give different answers about whether those events were simultaneous. That disagreement is not a quirk of bad measurement. It's built into the geometry of space and time. There is no absolute now, shared by everyone, ruling out the idea that there could be a universal present slice of the universe that everyone would agree on. Events that are simultaneous for one observer can be ordered differently for another. This is called the relativity of simultaneity, and it points to a radical consequence. Our division of reality into past, present, and future depends on your motion. If simultaneity is observer-dependent, then what counts as the present isn't a universal feature of reality. Once you accept that, a natural picture emerges. Think of the universe like a block of spacetime, where time is just another dimension alongside the three of space. This is the block universe idea. Instead of thinking of the universe as something that exists only in the present and then changes, imagine a four-dimensional object where every event, every moment of your life, every rock's fall, every star's explosion, is a point in this spacetime block. The past exists as much as the future. They are simply other regions of the block located at different positions along the time dimension. A convenient analogy is a movie film. A single film strip contains all the frames of a movie. Each frame is like a moment: the opening scene, a middle scene, the ending. When the film is sitting in a box, every frame is already there. You can run the film through a projector and experience a flow, but that flow doesn't mean the frames didn't already exist. In the block universe, the projector is our consciousness moving along what we call time, producing the sensation of flow. The film strip analogy isn't perfect. Consciousness isn't literally a projector moving along a strip, but it helps capture the idea that all moments could exist equally while we experience them in sequence. This philosophical stance that all times are equally real is called eternalism. Eternalists say that the past, present, and future are all part of a four-dimensional reality. By contrast, presentism is the opposite idea. Only the present is real, and the past and future don't exist in the same sense. There's also a middle ground called the growing block view. The past and the present are real, but the future doesn't yet exist. As time passes, new slices get added to the block. Each of these views tries to capture what we feel and how physics describes the world, but they handle existence differently. Special relativity lends strong conceptual support to eternalism. If there's no global present, why privilege any single slice of spacetime as the real now? If two observers disagree about which events are simultaneous, then either those disagreements are trivial, or the notion of a single objective present must be abandoned. Eternalism makes the math and the physics comfortable. All events already exist, and the different observers are simply slicing the block in different ways. That's why many physicists and philosophers of physics find the block universe attractive. It fits the geometry of relativity naturally. Beyond the abstract, there are practical demonstrations of time's strange geometry. GPS satellites are a great everyday example. They orbit Earth at high speeds and sit higher in Earth's gravitational field than we are on the surface. Both motion and gravity affect how time flows according to the theories of relativity. Satellites experience time slightly differently than clocks on the ground. The GPS system works only because engineers account for these relativistic time differences. Otherwise, navigation would drift by kilometers in just a few hours. That mismatch is an unmistakable real-world consequence of time being tied up with motion and gravity, not some independent universal ticking clock. The practical success of GPS doesn't directly prove the block universe, but it shows that the way we measure and compare times depends on frame of reference, which is a clue toward the relativity-driven picture. This raises an important question. If past and future both exist in the block, what do we make of the sense that time flows, that things change and the future is open? Is the flow of time a real physical process or an emergent illusion produced by memory, thermodynamics, and the way our brains work? To untangle this, it helps to separate different senses of flow. First, there's the metaphysical flow that some people mean. That time itself is a fundamental, dynamic thing that moves, carrying events from possibility into reality. Second, there's the experiential flow, the felt passage of time, the way your experiences have a before and after structure, and your memories are of a past that seems fixed. And third, there's the physical ordering of cause and effect, the fact that some events can influence others only if they're earlier in time, which is a practical asymmetry we rely on. Starting with physical laws, many of the fundamental equations, Newton's laws, Maxwell's equations, the Schrödinger equation in quantum mechanics, are time-symmetric. If you take the movies of processes these laws describe and run them backward, the equations generally still hold. A planet orbit under Newtonian gravity looks like a planet orbit backward if you reverse time. The equations don't care about a direction. They treat past to future the same as future to past. That symmetry suggests there's nothing in those equations that insists time must have an intrinsic direction. Yet macroscopic phenomena show a clear arrow of time. You break an egg but never unbreak it. Heat flows from hot to cold until equilibrium is reached. Coffee cools down, not heats up spontaneously. That directional behavior is captured by the second law of thermodynamics. In an isolated system, entropy, a measure of disorder or the number of ways a system can be arranged, tends to increase. Entropy increase provides a thermodynamic arrow of time. The actual microscopic laws allow time reversal, but overwhelmingly more microstates correspond to higher entropy macrostates. Starting from a low entropy arrangement, the system will almost inevitably move toward greater entropy simply because there are many more ways to be disordered than ordered. So where did the low entropy initial condition come from? That's a big question that cosmology takes seriously. Our universe appears to have begun in a very special, low entropy state. Think of the smooth early cosmos shortly after the Big Bang. That condition set the stage for entropy to increase, which gives us the thermodynamic arrow we experience. Memories form, records are written, cause precedes effect in practice. In short, the arrow of time that animates our experience and everyday processes arises from boundary conditions, the initial low entropy start, rather than from time's equations themselves. Another arrow is the cosmological arrow. The universe is expanding. The expansion provides an overall direction that, at least historically, has been associated with the thermodynamic arrow. Radiation spreads out, structures form, stars ignite and die. There's also the radiation arrow. Waves and signals typically spread outward from sources, and the causal arrow. Influences propagate within the limits set by the speed of light. All these arrows line up in the everyday world we know. But the feeling that time actually moves, that the future doesn't exist and the present is privileged, seems to be deeply connected to memory and consciousness. Our brains record events and create a temporal structure. Sensations now, memories of earlier sensations, expectations of later ones. Neurologically, the brain is a system that creates a narrative ordering of experiences, integrating past information to predict and respond to the present and near future. Cognitive science shows that memory formation itself is an irreversible process. Creating a stable memory requires dissipating energy and increasing entropy somewhere in the brain or environment. So the subjective sense of flow may be rooted in physical, thermodynamic processes in our neural machinery. In other words, the flow might be something the brain constructs while operating within a universe that has an entropy gradient. If flow is a construction, does that mean it's an illusion? Illusion is a loaded word. The felt passage of time is a real phenomenon in the brain, not fake, but it may not correspond to an objective, global physical process called becoming. Saying it's an illusion is like saying the colors we see are not intrinsic properties of electromagnetic waves, but perceptual features produced by our visual systems. The colors are real experiences, even if their existence depends on the biological processing of light. Likewise, the passage of time could be a real feature of our experience without being a fundamental property of the universe. Now let's bring quantum mechanics into the conversation, because many people think quantum theory gives room for open future. That indeterminacy at the microscopic level might restore a sense of becoming. At first glance, quantum mechanics does introduce fundamentally probabilistic outcomes. Before measurement, a system is described by a wave function that encodes probabilities for different outcomes. When a measurement is made, standard interpretations say the wave function collapses into a definite state with some probability. That collapse is often thought of as a real, time-asymmetric event. Possibilities become fixed outcomes. However, the interpretation of quantum mechanics is a hotly debated topic. Some interpretations keep a block universe-style picture intact. The many worlds interpretation, for example, treats the universal wave function as evolving deterministically and unitarily according to Schrödinger's equation. There's no collapse. Instead, the universe branches into multiple, non-interacting histories where all possible outcomes occur. In that view, the block is even bigger and contains all branches. Each branch has a consistent timeline. Other interpretations posit objective wave function collapse, which is time asymmetric and could be seen as a fundamental becoming. But these interpretations introduce new dynamics to explain how and when collapse happens, and they're experimentally contentious. So quantum mechanics doesn't offer a decisive blow either way. It depends on which interpretation you adopt. There's also a subtle line of thought involving quantum experiments that play tricks with causality-like phenomena, such as delayed choice experiments or quantum erasers. These experiments show that, in quantum systems, present measurements can change the kinds of correlations we see in the past when looking at joint statistics. That sometimes gets phrased as the future affecting the past, but that phrasing is misleading. What these experiments really show is that quantum correlations can be non-classical, and that our descriptions of events often depend on what measurements we perform. They don't let you send a message into the past or create logical paradoxes. Causality, the idea that signals can't go faster than light or be sent into the past, remains intact in ordinary quantum mechanics and relativity. The block universe view can feel chilling to some, because it seems to render our future choices pre-existent and fixed, like scenes already painted onto the film. But we should be careful about conflating already located in spacetime with causally predetermined in a problematic way. Even in a block universe, causation has a direction through a structure called light cones. From any event, you can draw a cone that divides spacetime into the future that can be influenced by that event, the past that could have influenced it, and everything else that can't be causally connected, the elsewhere region. The light cone enforces causal order. You can't cause something outside your future light cone. So in practice, actions have consequences that make sense, and reasoning about causes and effects remains meaningful. Another way to approach the worry about free will is to recognize different philosophical notions of free will. Many philosophers defend a compatibilist view. Free will is about acting according to your desires, reasons, and character, not about being metaphysically uncaused. Under compatibilism, whether the block universe is real or not doesn't undermine moral responsibility or the meaningfulness of choices. From our subjective point of view, we deliberate and choose, and those deliberations are part of the spacetime structure whether we like it or not. If you prefer a version of free will that requires indeterminacy to truly open the future, then your considerations will tie into the interpretation of quantum mechanics. Only interpretations that include genuine indeterministic collapse would support that kind of libertarian free will. But those interpretations have their own problems and aren't universally accepted. There's also an approach that treats time's flow as an emergent macroscopic phenomenon arising from complex systems. Imagine a 3D video game world stored on a hard drive. The game state at each tick of the simulation is recorded in some data structure. The simulation doesn't have to push reality into existence over time. It merely contains a series of states. But when the simulation runs in real time, players experience events unfolding. An observer inside the simulation would experience a flow. The point is that dynamics and flow can be real to observers embedded in a system without requiring time to be fundamental. In physics, some researchers explore similar ideas. Time and its arrow might emerge from entanglement patterns, thermodynamic gradients, or coarse graining over microstates, producing an effective, emergent temporality at macroscopic scales. Let's look at a few intuitive examples to ground all this without too much formalism. Picture a closed room with a bunch of ping-pong balls on a tabletop, arranged neatly. You blow on them and they scatter into a messy arrangement. The neat initial state is very special. There are relatively few ways to be neat, but astronomically many ways to be messy. Statistic rules say you'll almost always see the system evolve toward messiness, not neatness. The laws of motion governing each ball didn't favor one direction. The difference comes from counting microstates. If you had a complete record of every ping-pong ball at every moment, a full space-time description of the room, you could plot it as a set of points in the block. The neat to messy direction in time corresponds to the part of that block where entropy increases. An observer in the room, making memories, will perceive a flow from neat to messy. The block contains both the neat initial configuration and the later messy arrangement. The flow is a perspective-based description tied to the direction of entropy increase. Now take the idea of memory. A memory is a physical record, patterns in neural connections, chemical states, or structures that are correlated with past events. The directionality of memory is such that we have records about past states but not about future states. That asymmetry links to thermodynamics. To write a record, you typically need to consume energy and increase entropy. So remembering is a thermodynamic process. The asymmetry of memory, we remember the past, not the future, creates a strong experiential sense of flow and of the past being fixed and the future open. At this point you might wonder, if eternalism is true and the future is as real as the past, then why don't we have memories of the future? Under eternalism, future events exist in spacetime, but the physical processes that yield memories are located earlier in time relative to those future events. To have a memory of a future event would require a record in your brain that is correlated with something in your future light cone. That would mean backward causation, or a violation of causal constraints. In our universe's structure, such correlations don't arise in the usual way because of the thermodynamic and causal arrows aligning, so we don't remember the future. Eternalism doesn't imply that we have records of the future. It only implies those future events are part of spacetime's four-dimensional manifold. Some people find the block universe picture metaphysically unsatisfying because it seems to make time unreal. Others find it liberating because it removes the need to explain how the future becomes real. It already is. There's a pragmatic angle too. Regardless of the deep metaphysical truth, physics uses a time parameter in equations to predict outcomes, and those predictions work extremely well. Whether time is flowing at the fundamental level doesn't change the immense practicality of treating time as an ordering parameter for events. Let's also touch on general relativity, because it gives a richer picture than special relativity. In general relativity, mass and energy tell spacetime how to curve, and spacetime curvature tells matter how to move. Time and space are woven together in a dynamic fabric. That fabric can be warped so strongly that what looks like time and space interchange roles near certain extreme objects, like black holes. In regions with strong gravity, clocks run at different rates depending on depth in the gravitational well. That's why time dilation near massive objects isn't just a tiny novelty. It's a real effect with consequences for the structure of spacetime. General relativity still treats spacetime as a four-dimensional geometry, further supporting the geometric, block-like view of the universe. Yet general relativity also has solutions that are weird, like closed time-like curves in some exotic spacetimes, where in principle you could travel into your own past. Such solutions lead to paradoxes and are generally thought to be unphysical or at least not realized in our universe. Most realistic cosmological models avoid these issues, and causal structure remains well behaved. A point worth emphasizing is that even if all times are equally real, the description of the universe can still be dynamic when viewed from a particular frame. Think about standing at a train station. The schedules, the timetable, the arrival and departure times matter to you. Even if the entire timetable exists as a block, the experience and practical consequences are dynamical. Societies plan, people make promises, reason about future contingencies, and act to change outcomes. This practical dynamism is not erased by eternalism. It's simply grounded in the relations between different spacetime events. There's also an intriguing idea that the flow of time might be nothing more than a thermodynamic or informational bookkeeping practice. Consider the way lawyers write contracts with dates. A contract has terms that are implemented at different times. Those dates are labels on portions of the block. When the date passes, events specified by the contract are embedded in the block. The legal system doesn't rely on metaphysical passage. It relies on records, deadlines, and causal enforcement. From this angle, time is a useful parameter for organizing events and making causal connections intelligible. The philosophical debate is large, and some of it pivots on the semantics of exist. Does it mean is located at some spacetime point, or is causally efficacious now? Eternalists typically adopt a locational notion. Events exist if they occupy spacetime points. Presentists adopt a stronger, tense-based notion. Existence is tied to the present tense. Which notion is more satisfying partly depends on your metaphysical preferences and partly on how compelling you find the arguments from physics, especially the relativity of simultaneity. For scientists trained to accept relativity's lessons, presentism is awkward to maintain because it requires positing a privileged global present that relativity says doesn't exist. Some presentists respond by trying to build a preferred foliation of spacetime into a present using extra physics that breaks Lorentz symmetry. But that would require new empirical evidence supporting a preferred frame, evidence we don't have. So where does that leave us? We've seen that Einstein's relativity gently pushes us from a single universal now to a picture where simultaneity is relative, and a four-dimensional spacetime is a natural representation. That representation leads toward eternalism and the block universe as attractive models for thinking about time's ontology. Yet the experienced flow of time is powerful, tied to memory, thermodynamics, and the functioning of brains. Quantum physics complicates the story. Depending on interpretation, it may put indeterminism back into the picture, or it may simply enlarge the block. Philosophically, there are still lively debates about free will, existence, and what it even means for something to be real in time. To delve further into the question, it helps to consider some concrete thought experiments and practical phenomena that highlight where the tension lies between the mathematical elegance of the block and the messy, lived reality of becoming. Imagine you are an astronaut floating in deep space with a precise clock. You drift by a planet and choose to detonate a small explosive device at some coordinate. That detonation is an event in spacetime. If you later chart your trip and map out your world line, the path you trace through spacetime, that detonation is at a particular point on your world line. Now imagine somebody else, a friend moving at a different speed, reconstructing the spacetime and plotting their own world line. Both you and your friend can agree on the invariant spacetime interval between events and on causal relationships, even if you disagree about which events are simultaneous with which. The physical facts, the coordinates of events in spacetime and the causal connections, are invariant in the sense defined by relativity. You and your friend can predict what instruments will read at different points and can test those predictions. Those predictive successes give weight to the idea that spacetime is the right arena for physics. But now think about your subjective experience of deciding whether or not to trigger the explosive. For you, it feels like a choice that happens at a particular time. You might deliberate, and that deliberation takes place across a slice of your brain's processing over some time interval. Those physical states of your brain are embedded in spacetime, and if you're an eternalist, you'd say those states are fixed points in the block. But from your first-person perspective, you feel free to choose. Your experience is temporally extended and arrowed in a way that is intimately tied to the thermodynamics of how your brain works. If the block universe picture makes you uneasy, remember that it doesn't erase the causal efficacy of your actions or the usefulness of reasons-based explanations in psychology and ethics. It just grounds them differently. To get a firmer grip on whether we should regard time as fundamentally flowing, some philosophers distinguish two competing families of metaphysical theories, the A theory and the B theory of time. The A theory tries to capture the reality of the present moment, the passage of time, and the openness of the future. It affirms that tensed facts, things being past, present, or future, are metaphysically important. Presentists typically align with A theory. The B theory, by contrast, treats temporal relations as tenseless. Earlier, then later than, and simultaneous with are all fundamental and objective, but there is no objective moving present. Eternalists and block universe advocates tend to side with B theory. Physics, especially relativity, has been taken by many to favor the B theory because of the absence of global simultaneity, but not everyone is convinced. Some philosophers argue that our best physics is compatible with a kind of moving present if you add additional structure, though that structure currently lacks experimental support. Another important consideration is the role of practical time in our scientific models. Even if the fundamental ontology leans toward a block, our scientific and everyday lives proceed by modeling time as flowing. We set schedules, engineer systems that react in real time, write software that depends on temporal sequencing. The usefulness and explanatory power of a flowing time model should not be dismissed just because a more abstract description sees everything laid out. Physics often has multiple levels of description, microscopically precise but less intuitive models and coarse-grained, phenomenologically effective models. Temperature is not a fundamental quantity in quantum mechanics. It emerges from ensembles. Likewise, the flow of time might be emergent and perfectly real at certain levels without being fundamental. Now, a few readers might object. If the future exists, couldn't I go and read a book that tells me what will happen next week? In a block world sense, if the future event where the book contains next week's outcome exists, then in principle someone could know it. But the practicalities of how information is distributed and how memories form make this impossible without causal paradoxes. Any physical device that reliably transmitted information backward in time so we could predict the future would enable all kinds of paradoxical scenarios and would likely violate causality or the laws of thermodynamics as we understand them. So while the future being there doesn't imply we can access it in advance, it also means that the future is in some metaphysical sense present in the spacetime fabric. The constraints of physics make it so that we can't exploit that structure to violate causal order. The idea that we might need a meta-time, a time in which time itself flows, is also sometimes raised. If time flows, what is it flowing in? Does a meta-time pass, carrying the primary time along? That leads to infinite regress. A meta-time would be needed for the meta-time to flow, and so on. This regress argument is often used to argue that the flow of time can't be a fundamental feature requiring a second time dimension. Instead, if flow exists, it must be emergent or reducible to other physical processes. The block universe picture avoids this regress by not positing any literal meta-time. We should also touch on how different cultural and linguistic frameworks treat time. Some languages encode time differently in metaphors and grammar. Some cultures conceive of time cyclically rather than linearly. These human perspectives influence how strongly we feel that time flows. Cognitive science shows our temporal intuition is shaped by embodiment, social practices, and language, again, reinforcing that the feeling of flow is intimately tied to our situated existence. In more speculative areas, physicists have explored models where time's character is altered or emerges from more fundamental, non-time-based structures. Approaches in quantum gravity, attempts to reconcile general relativity and quantum mechanics, sometimes treat time differently. For instance, in some formulations, spacetime as a continuum is emergent from more primitive entities, and time could be a parameter that only makes sense at scales where those entities coarse-grain into smooth geometry. Loop quantum gravity, causal set theory, or certain holographic ideas in string theory provide various sketches of how spacetime might arise from pre-geometric building blocks. These are active research areas. They don't yet offer a definitive picture, but they suggest that time might no longer be a fundamental ingredient in the deepest description of reality. If that turns out to be true, then both eternalism and other classical notions of time would need to be reinterpreted in the new framework. All this shows why the question, "Is time an illusion?" is so stimulating. It's not a yes or no question in any trivial sense. The experience of time is real, grounded in the brain and thermodynamics. The mathematical frameworks of modern physics reframe our metaphysical intuitions, often toward a block-like view, and quantum mechanics complicates the picture, offering both deterministic and indeterministic readings depending on interpretation. The debate brings together physics, philosophy, neuroscience, and even everyday experience. As we keep exploring, one useful attitude is to be pluralistic, accept that different layers of description can be true in different senses. At the level of spacetime geometry, the block universe is a powerful and consistent way to understand events and causal structure, especially given relativity. At the level of thermodynamics and biology, the ebb and flow of time are real and indispensable for explaining memory, decision-making, and history. At the level of human existence, the passage of time is central to how we live and plan. Next, it would be helpful to examine some concrete objections and thought experiments that push against the block universe view. For example, arguments from presentists who claim we have privileged access to the present, or challenges invoking free will, and see how those objections fare against the physics and the metaphysics we've discussed. Then we can dive into how current physics research, especially in quantum gravity and the study of black holes and cosmology, might shift the ground under these debates. Finally, we'll want to consider what all of this means for everyday life. How to reconcile living in a world where future and past are both meaningful with the way we actually make choices, remember, and plan. So what do these big ideas mean when they bump up against our everyday lives? The plans we make, the choices we agonize over, the memories we treasure. To get a better grip, let's tackle some of the sharper objections people raise against the block universe picture, and the idea that time might be, in some sense, illusory. Then we'll move into how current physics wrestles with time at the cutting edge, black holes, quantum gravity, and what happens when we try to mash up general relativity and quantum mechanics. Along the way, I'll toss in concrete examples and experiments, because these philosophical worries often get sharper when you press on real-world facts. One of the most persistent objections comes from the undeniable force of our direct experience. Right now feels different from a minute ago or a minute from now. That nowness is vivid. There's a slice of experience that has the distinctive character of being present. Presentists take that seriously and say, the present is all that exists. The past is gone. The future is not yet. This is an appealing view because it matches how things seem from the inside. Philosophers counter by asking whether that feeling can be used as a metaphysical arrow. Does a phenomenological fact about experience force an ontological claim about the universe? You can answer either way, but physics pushes against presentism, because relativity makes it hard to define a single global present. Different observers slice spacetime differently. That doesn't mean the feeling is false. It means the feeling probably has a biological and thermodynamic explanation, even if it doesn't map onto a privileged fundamental slice of the cosmos. To make that issue more concrete, consider the cosmic microwave background, the faint microwave glow left over from the Big Bang. If you measure its temperature in different directions while you're at rest with respect to the average motion of matter in the universe, the CMB looks the same in every direction. Observers moving relative to that rest frame see a dipole anisotropy, a hot spot in one direction and a cold spot in the opposite direction. In cosmology, physicists often pick out that CMB rest frame and define cosmic time as the proper time that elapses for observers at rest with respect to the expanding universe. This gives you a convenient global slicing. Every event in the universe can be assigned a cosmic time coordinate corresponding to how long since the Big Bang in this preferred frame. Some people seize on that and say, see, we do have a natural universal now after all, it's the slice of constant cosmic time. But that move is tricky. The cosmic time slicing depends on the actual distribution of matter and radiation in our universe. It's not a metaphysical necessity coming from deeper principles. It's a pragmatic, coarse-grained, useful choice, one that works because our universe is, to a good approximation, homogeneous and isotropic on large scales. It also privileges a convenient frame without overturning relativity's lesson. Local observers moving at different velocities still disagree about simultaneity in general. Another worry is that if the future already exists, then what am I doing when I deliberate? Philosophers and psychologists have long debated whether free will is compatible with determinism. There are a few ways to handle that. Compatibilists argue that free will is about acting for reasons, forming intentions, and responding to motivations, not about being uncaused atoms bouncing randomly. On that view, whether your future actions occupy locations in the block doesn't undercut the meaningfulness of choice. Imagine you choose between coffee and tea. Your reasons, your desires, the way your brain evaluates options are physical processes that have causal effects. Those processes are part of the block. The fact that they are located in spacetime doesn't mean they aren't your decisions. The other major position, incompatibilism, says that if the future is fixed, then true free will is impossible. Some incompatibilists try to recover free will by appealing to indeterminism in quantum mechanics. But as we'll see, quantum indeterminism isn't an automatic ally of libertarian free will. Randomness doesn't equal control. That brings us to quantum mechanics, where the temptation is strong to hope that the theory restores openness to the future. At first glance, it seems promising. Quantum events are probabilistic, so maybe the future isn't fixed. Look under the hood, though, and the picture is messier. There are multiple interpretations of quantum mechanics that treat time differently. The Copenhagen-style textbook interpretation talks about wave function collapse upon measurement, which introduces a time asymmetric process. Possibilities become an actuality. If that collapse is an objective physical process, it might provide a real kind of becoming. But the details of collapse, when and how it happens, are fuzzy in the standard reading. Some versions, like GRW, Ghirardi-Rimini-Weber, objective collapse models, try to make collapse precise and physical. They posit new dynamics that break time symmetry. Those models are empirically constrained but not ruled out, and they do offer a picture of an open future. The many worlds interpretation keeps the Schrödinger equation's deterministic evolution and denies collapse. Instead, all outcomes occur in branching, non-interacting branches of the universal wave function. If you accept many worlds, then the block gets bigger. Every branch is part of the overall history. Some people find this liberating because probabilities are explained as subjective uncertainty about which branch you will observe. Others find it ontologically excessive. There are also retrocausal and time-symmetric interpretations that try to explain quantum correlations by allowing influences that run both forward and backward in time, such as the two-state vector formalism. These approaches can be mathematically consistent, but are controversial and require careful bookkeeping to avoid paradoxes. So quantum mechanics can be read in ways that are compatible with a block universe or ways that introduce an objective becoming. The experimental facts themselves, interference, entanglement, Bell inequality violations, decoherence, do not yet force a single definitive metaphysical picture. That's one reason the foundations of quantum mechanics remain lively territory. A related, and often surprising, experimental result concerns time symmetry in particle physics. Most of the fundamental laws appear nearly symmetric under reversing the direction of time. You can take many microscopic processes and run them backward in time, and the equations look similar. But there are exceptions. Experiments with certain kinds of subatomic particles, kaons and B mesons, show CP violation, which by the CPT theorem implies a violation of time reversal symmetry, T-symmetry, at the microscopic level. That means, strictly speaking, the universe's laws are not perfectly time-symmetric. The effect is extremely subtle and has nothing to do with the macroscopic arrow of time we live with, but it does indicate that the symmetry between past and future is not absolute at the most fundamental level. Let's shift to another hard part of the story, the thermodynamic arrow of time, and why the early universe seems to have been in a very special low-entropy state. If entropy increase is what underlies the directionality we experience, then why did the universe start so ordered? Physicist Roger Penrose brought attention to gravitational degrees of freedom here. A smooth, nearly uniform distribution of matter, like the early universe seen in the cosmic microwave background, is actually low gravitational entropy. There are few ways for mass energy to be arranged as a smooth soup compared to the many possible ways it can clump and form black holes. Gravity wants to clump, and clumping vastly increases the number of microstates associated with the mass distribution. Penrose argued that the Big Bang's low gravitational entropy is the real mystery requiring explanation. It sets the stage for entropy to grow and for a thermodynamic arrow to emerge. Inflationary cosmology provides mechanisms that can make the early universe remarkably smooth and low entropy in some senses, but the ultimate origin of the universe's low entropy boundary condition remains an open question that researchers actively explore. Black holes make the plot thicker. In the 1970s, Bekenstein and Hawking discovered that black holes behave thermodynamically. They have an entropy proportional to the area of their event horizon and a temperature related to surface gravity, and they emit Hawking radiation. Those discoveries hint at a deep relationship between geometry, information, and thermodynamics. If spacetime geometry itself carries entropy, then the arrow of time might have roots in gravitational microphysics. Moreover, black holes raise acute puzzles about how information behaves. Famously, the black hole information paradox asks whether quantum information that falls into a black hole is destroyed once the black hole evaporates. Resolving those puzzles will likely reshape our view of time, causality, and the ultimate nature of physical law. When we try to quantize gravity, to develop a quantum theory of spacetime, we encounter what's often called the problem of time. In some approaches, like the Wheeler-DeWitt equation, the formalism that attempts to describe the quantum state of the universe doesn't contain an explicit time parameter. The equation is timeless in appearance. It's a constraint rather than a dynamical evolution in an external time. That sounds alarming at first. How can anything change if the fundamental equation is timeless? One strategy to deal with this is relational time. Pick one part of the system to serve as a clock and describe evolution of other parts relative to that clock. In this view, time emerges from correlations between subsystems. One subsystem's changing state provides the clock reading against which you measure changes in another subsystem. The Page-Wouters mechanism is an example of this relational idea. These moves are philosophically and technically subtle, but they suggest that time as we experience it might be an emergent, relational construct rather than a fundamental background parameter. A complementary line of thought comes from the holographic principle and the ADS/CFT correspondence in string theory. In those frameworks, a lower-dimensional quantum theory without gravity can encode a higher-dimensional spacetime with gravity. Space, and possibly time, can be emergent from more primitive quantum degrees of freedom. If time emerges from a more foundational layer, then notions like the block universe must be reinterpreted in the emergent language. Maybe the block is a good description at scales where spacetime is smooth, but at the Planck scale, time dissolves into a web of quantum relations. All of this research suggests that our ordinary intuition about time, a single, universal rate, a flowing present, is not a solid guide to the deep structure of the world. But we also shouldn't throw intuition out with the bathwater. The way we organize lives, carry plans, and hold people accountable depends crucially on temporal relations. The law treats causal chains seriously. Contracts require performance by certain dates. Causal responsibility presupposes a temporal ordering of actions and consequences. Those practical uses of time are robust and necessary. To illustrate how the block viewpoint and practical living can coexist, think about a courtroom. Evidence, witness testimony, and logs are used to reconstruct what happened in the past and to attribute responsibility. Even if, at a metaphysical level, past and future are equally real, in the block, the procedures of the law depend on causal chains, records, and predictability. A defendant deliberated, acted, and produced effects. Those processes are physical and have causal consequences that can be investigated. Whether those events are located in a four-dimensional block doesn't change the meaningfulness of punishment, rehabilitation, or reward. So for social systems like law, ethics, and planning, the block universe is hardly paralyzing. It's simply the backdrop against which causal stories are told and enforced. Neuroscience helps explain why the present feels so vivid. Our brains are prediction engines. They constantly use past sensory input to generate expectations and to interpret incoming signals. The brain's architecture creates a stream of conscious experience with a built-in direction. Sensory input arrives, neural circuits integrate evidence, memories are accessed, and a narrative unfolds. Experiments such as the famous Libet studies showed brain activity related to an action sometimes precedes the subject's reported conscious decision to act. These findings have been used to challenge simplistic notions of free will. But the contemporary interpretation is more nuanced. Brain processes are distributed, decisions often build up over time, and the emergence of conscious awareness is itself a process that taps into ongoing neural dynamics. This doesn't straightforwardly dissolve responsibility. It reframes it as a phenomenon emergent from complex brain mechanisms that are themselves embedded in social and biological contexts. Memory itself is an instructive case. Memories are not static snapshots. They are dynamic, reconstructive processes. When you remember an event, your brain reactivates patterns associated with it, and in doing so it can alter the memory. That's why eyewitness testimony can be unreliable, and why memories can be manipulated or fade. The asymmetry between past and future in memory is tied to how records are written. Forming a stable memory generally involves dissipating energy and changing the state of the brain in a way that's hard to reverse, another manifestation of the thermodynamic arrow. The fact that records are asymmetric, you have records of the past but not of the future, contributes strongly to the psychological sense that the past is fixed and the future open. Let's examine a few thought experiments that drill down into where the blocking intuition gets uncomfortable. One simple toy example is the diary test. Suppose you keep a detailed diary that records your decisions, your feelings, and events. If future events are already located in the block, then your diary entries are too. If you open the diary on Monday, you read what you wrote on Sunday. That seems ordinary. But imagine if you could read a diary entry that records something you're going to decide next week. Would that show the future is fixed? The answer depends on causal accessibility. For the diary to be reliably correlated with an event in the future, there must be a physical mechanism transmitting that information backward in time or a pre-existing correlation set up earlier, both of which would be extraordinary and would likely enable paradoxes like changing the recorded outcome by acting differently. Physics seems to forbid such cheap access to the future. Causal structure and thermodynamics conspire to keep records pointing backward and not forward. People sometimes toy with the idea of a metatime to rescue the notion of flow. If time flows, maybe it flows in some second, higher-order time. That move quickly produces an infinite regress. The metatime would itself require another meta-metatime to flow, and so on. That's one reason many philosophers and physicists prefer to explain flow as an emergent property of systems operating within time, rather than positing a separate external temporal dimension. You can have a real, robust sense of change and passage without needing a metaphysical conveyor belt of moments. Another thought experiment concerns bets and prediction markets. Imagine you place a bet on tomorrow's lottery number. If the future were already determined in the block, someone might object that bets are pointless because the outcome is fixed. But bets are meaningful because of epistemic uncertainty. You don't know the future, and your decision to place a bet has causal effects on your present state, your money, your anxieties, and on other agents. Whether the outcome is metaphysically fixed doesn't change the practical importance of learning, prediction, and decision-making. In many formal frameworks, including deterministic physics, probability is still a useful tool that expresses uncertainty about initial conditions or coarse-grained states. Let's bring in a concrete experimental demonstration of relativity's impact on time that affects our daily lives: GPS. The satellites that provide GPS signals are moving fast relative to ground receivers and are higher in a gravitational potential well, so they experience time slightly differently. Engineers must correct for both special relativistic time dilation, due to their orbital speeds, and general relativistic gravitational redshift, because clocks higher up run faster relative to clocks on the ground. The system works only because we understand and correct for these relativistic effects. That's a good reminder. Whether or not the block universe captures the ultimate metaphysics of time, physics' treatment of time as a geometric component of spacetime yields invaluable practical results. There are also striking lab experiments probing time in quantum settings. Delayed choice experiments and quantum erasers sound exotic because they seem to allow present measurements to affect how we should describe earlier events. But those experiments don't allow you to change recorded outcomes in the past or send information backward in time. What they show is that in quantum mechanics, the kinds of correlations you observe depend on the complete experimental arrangement, including what you choose to measure later. It shifts our classical intuitions about fixed, pre-existing properties, but it doesn't hand you retrocausal control in a way that violates causality or allows time travel paradoxes. Finally, let's touch on what the research directions I've described might mean for our broader perspective. If future work in quantum gravity shows that time is emergent, that spacetime, including time, arises from underlying quantum or informational relationships, then both the block view and presentism will need to be translated into that new language. Perhaps the block emerges at scales where spacetime is smooth, while at a more fundamental level there are only relations among quantum degrees of freedom. That would mean the question, is time an illusion, is too crude. Instead, we'd ask, At what level is time a useful, robust concept? At what level does it fade away? And what aspects of temporal experience are robust across scales? All of this is to say, time's philosophical status is entangled with physics, neuroscience, and practical human concerns. The block universe offers a neat, geometrical picture that follows directly from relativity's lessons, and it's a useful way to think about events and causal structure. But our lived sense of flow, the thermodynamic arrow that orders experience, and the brain mechanisms that generate memory and anticipation are all real processes that give time its psychological force. Quantum mechanics complicates matters and offers routes both to restoring genuine openness and to enlarging the block, depending on interpretation. And when we try to unify gravity with quantum theory, time becomes even stranger, sometimes disappearing from fundamental equations and sometimes reappearing as an emergent correlation. So where does curiosity lead us next? It's natural to want to press on the knots where metaphysics and experiment tug in different directions. We can dig deeper into presentist strategies and their responses to relativity. For example, whether a preferred slicing of spacetime could be physically motivated, and examine whether quantum indeterminism really helps free will. We can also look more closely at the latest ideas from quantum gravity and black hole thermodynamics, because those are the places most likely to force us to rethink what time means. In the next stretch, we'll examine some of those current proposals and their experimental prospects, and we'll walk through a few more thought experiments that test our intuitions about causation, prediction, and personal agency. If you want to see where the debate about time gets interesting right now, you have to look at the places where gravity and quantum physics collide. That's where our neat pictures, the block universe, the thermodynamic arrow, the feel of now, start to tangle, and where different researchers are trying to push physical ideas into testable territory. Let's walk through some of the main proposals and the experimental and thought-experimental tools people use to probe them, keeping the intuition front and center. One class of approaches begins with canonical quantum gravity ideas and the famous problem of time. When people try to write a quantum version of general relativity, the theory where spacetime itself curves, they often end up with equations that don't contain a usual time variable the way other quantum equations do. A well-known example is the Wheeler-DeWitt equation, which roughly says that the geometry of the universe satisfies a constraint rather than evolving in an external time. To a physicist, that looks like nothing happens at the fundamental level. That sounds absurd, but there's a way through. Treat time relationally. Pick some physical system inside the universe to act as a clock, a particular set of degrees of freedom, and describe how the rest of the universe changes with respect to it. In other words, time becomes an internal parameter measured by change in other things. This idea, that time is emergent from correlations among subsystems, is conceptually tidy because it avoids adding an external clock and meshes with the thought that spacetime might be an emergent entity. But it's also technically messy. Choosing a good clock that behaves nicely and showing that this construction reproduces the usual notion of time in all relevant circumstances is hard. Causal set theory offers a different angle. Here the basic picture is that spacetime is fundamentally discrete, made of elementary events sprinkled in a way that preserves the causal order, who can influence whom. Those events form a partially ordered set, a causal set. One can then attempt dynamics where new elements are added in a stochastic, sequential way. That dynamics naturally has a growing character. The causal set grows by accretion of new events. To some minds, this looks like a precise mathematical implementation of the growing block idea. The past and present accumulate, but the future does not yet exist. It's attractive because the growth process can be defined in a Lorentz invariant way. It doesn't pick out a rest frame, but the resulting models are primitive and still far from a complete description of our universe. Nevertheless, these attempts illustrate an important point. It's possible to invent theories in which a kind of objective becoming is built into the dynamics, and to check whether those theories are compatible with other physical principles. String theory and holography take yet another tack. In certain calculable settings, notably the ADS/CFT correspondence, a quantum theory without gravity living on a boundary can encode a spacetime with gravity in one higher dimension. That remarkable connection suggests space, and even time, might be emergent phenomena coming from more fundamental quantum degrees of freedom. People working in this area have even linked the growth of quantum complexity. Roughly, the difficulty of describing a quantum state using elementary operations, to the growth of certain spacetime features like the interior volume of black holes. If complexity grows in one direction, it gives a kind of arrow that mirrors the thermodynamic arrow. That's an example of how deep theoretical work can hint that the directionality we experience, and maybe the sense of flow, could be a manifestation of underlying quantum information theoretic processes rather than a primitive property of the universe. Black holes are a crucial testing ground for all these ideas because they sit at the crossroads of quantum theory, gravity, and thermodynamics. One reason black holes are so illuminating is that they behave thermodynamically. They have an entropy proportional to their horizon area and a temperature due to quantum effects, Hawking radiation. Those facts led to one of the great puzzles of modern physics, the black hole information paradox. If a black hole evaporates completely via thermal radiation, and that radiation looks thermal, random, what happens to the information about the stuff that fell in? If information is irretrievably lost, then quantum mechanics standard rules, which preserve information in unitary evolution, are violated. That raises questions about the nature of time, because unitarity is tightly linked to time evolution in quantum theory. Recent progress has been striking. Using semi-classical gravity combined with quantum information ideas, researchers have shown how the entropy of an evaporating black hole could follow a pattern, the Page curve, compatible with information being preserved, not destroyed. A central conceptual move in these calculations is the appearance of islands, regions of spacetime that, when included in the quantum extremal surface prescription, change which degrees of freedom you count as belonging to the radiation or to the black hole. The upshot is that, under plausible assumptions, the entropy of the radiation can start decreasing at a certain point, indicating that information is not lost. These results point toward a picture in which quantum correlations and spacetime geometry conspire to ensure consistency. They don't give a full microscopic account yet, but they suggest that time evolution and information flow in gravity are subtle and deeply quantum. What does that have to do with the flow of time? Two things. First, if spacetime geometry and information are intimately linked, then arrows of time, thermodynamic, causal, computational, might arise from the ways information is arranged and processed in the universe. Second, the resolution of paradoxes like the black hole information problem might require rethinking how we speak about events and histories in spacetimes with quantum features. Both directions point toward the idea that any full account of time will likely involve quantum information ideas and will blur the distinction between geometry and bookkeeping of correlations. On the experimental front, people are designing clever ways to test whether gravity behaves quantum mechanically and whether collapse-like processes happen in nature. One promising route is to try and put increasingly large systems into quantum superpositions, the way delicate molecules have been made to display interference. Over the last 2 decades, experiments have pushed interference experiments from simple atoms to molecules with thousands of atomic mass units. The plan for the coming decades is to attempt superposition with small but massive objects, small spheres or mechanical resonators, to see whether quantum mechanics holds at scales where gravitational effects start to matter. If quantum superposition holds up as mass increases, that supports the view that quantum theory applies universally. If superpositions break down in ways that can't be explained by environmental decoherence, that could point to an objective collapse mechanism, such as the GRW models, or to gravitationally induced collapse, a suggestion by Penrose, where gravity itself causes quantum states to choose a definite configuration. Those collapse models do make experimental predictions. For instance, Spontaneous collapse processes would slightly heat matter, create small amounts of radiation, or suppress interference in precise ways. Sensitive experiments, using cold atoms, interferometers, and carefully isolated mechanical systems, constrain the parameters of such collapse models. So far, mainstream quantum theory has held up under these tests, but the parameter space where collapse could still be happening is being steadily reduced. In parallel, there are proposals like the Bose-Marletto-Vedrel and other schemes that would test whether gravity can entangle two quantum systems. If two masses become entangled only via their gravitational interaction, that would be strong evidence that the gravitational field must be able to carry quantum information, i.e., gravity is quantum. Experimental groups are racing to make tabletop versions of these tests with microscale masses, separated by tiny distances and ultrasensitive detection. If such experiments succeed, they wouldn't directly answer metaphysical questions about the block or flow of time, but they would show that the quantum description extends into regions where spacetime curvature matters, nudging us toward frameworks where time is treated as a quantum-correlated entity. Let's step back to the thermodynamic side for a moment. The arrow of time we see, entropy increasing, has been usefully explained by pointing to the universe's low-entropy initial condition. But why was the early universe in such a special state? Cosmologists have layered candidate answers on top of each other. Inflationary cosmology provides mechanisms that make the early universe very smooth and nearly homogeneous. That helps explain a low gravitational entropy in one sense. Some researchers look for even deeper explanations, invoking ideas like a multiverse where many possible initial conditions exist and ours is selected anthropically, or cyclic models, where the universe undergoes repeated ekpyrotic contractions and bounces that reset the entropic bookkeeping. There are also more radical suggestions that the initial low-entropy condition is a law-like feature, a past hypothesis that should be taken as a boundary condition in the foundations of statistical mechanics. The choice among these views isn't settled. Part of the challenge is that empirical access to very early times is limited, though the cosmic microwave background and searches for primordial gravitational waves provide important clues. All these technical programs have philosophical implications. For instance, suppose a causal set or sequential growth model turns out to be the right description. That would seem to reinstate a kind of objective becoming. The universe literally grows. If, on the other hand, a holographic or Wheeler-DeWitt style framework where time is emergent wins out, then the blockish picture may be the most natural at the effective level, with the felt flow explained by lower-level processes. If experiments show gravity is quantum, that will push many people toward frameworks where geometry and quantum states are two sides of the same coin, reshaping our metaphors for time. None of these outcomes would trivially decide the question of whether time's flow is real, in the strong sense some philosophers mean, but each would change the landscape of plausible metaphysical interpretations. Thought experiments remain powerful tools because they push us to sharpen what we mean by real, flow, and open future. Consider the future diary variant. Imagine a device built before the present that reliably prints out tomorrow's lottery numbers. If that device existed and its outputs were reliable, that would be an extraordinary empirical discovery and would instantly alter our metaphysical conclusions. It would show either backward causation or pre-established correlations set up in advance. But physics, as we know it, tightly constrains this sort of behavior. Causal structure, statistical independence assumptions, and thermodynamic constraints prevent easy access to future information. The fact that our world resists manufacture of reliable future-telling devices is itself informative. It tells us about the causal architecture and the way correlations are produced in our universe. The block universe could perfectly well contain a record of tomorrows printed on paper, but creating such a record in advance without causal paradox would require mechanisms that physics denies. Neuroscience returns us to the human scale. Studies of brain processes related to decision-making show that a lot of what we call a decision is actually an extended physical process involving evidence accumulation, valuation, and response selection. Experiments where brain signals predict a simple action a little before the subject reports conscious intention, the Libet-type timing experiments, were once taken to challenge free will, but a more nuanced reading is that conscious awareness trails, and sometimes overlaps with, the brain's decision processes. If the world is a block and our choices are embedded within it, that doesn't negate the importance of reason's responsive control. The kind of free will that matters socially and ethically is not some mystical uncaused power. It's the ordinary capacity to act according to desires, deliberations, and intelligible motivations, capacities that the brain implements by physical processes. Whether those processes are prelocated in a spacetime manifold or arise dynamically is a separate issue. There are further philosophical puzzles that get sharpened by physics. One is the Boltzmann brain problem. If the universe lasts forever in certain statistical senses, then random fluctuations might produce self-aware brains that pop into existence with fleeting memories of a past that never happened. These Boltzmann brains would vastly outnumber normal observers under some models, leading to the worrisome conclusion that typical observers would be such fluctuations. Physicists use this kind of paradox to constrain cosmological models because we do not seem to be freak observers. The problem ties back to entropy and boundary conditions. The structure of the past and the way entropy evolves shapes what kinds of observers are typical. Another line of thought concerns personal identity and branching in quantum mechanics. In the many worlds picture, when a quantum event with multiple outcomes happens, the world branches and multiple versions of you appear, each observing a different outcome. That raises questions about how to understand future uncertainty. Before the branching, what does it mean to be uncertain about which outcome you'll observe? Some philosophers and physicists propose that uncertainty becomes a matter of self-location in a branching tree. You're uncertain about which branch you will occupy. That doesn't restore the past/future asymmetry of experience in a metaphysical sense. The branches all exist, but it does provide a framework for subjective uncertainty within a block-like ontology. It's an example of how different metaphysical positions can be compatible with ordinary decision-theoretic reasoning once you add the right conceptual machinery. What about empirical distinctions between presentist and eternalist ideas? Presentism can be rescued in principle if you postulate a preferred foliation of spacetime, a kind of universal now that slices the block into present moments. But that move breaks Lorentz symmetry, the heart of special relativity, unless the preferred slicing is hidden or otherwise constructed carefully. Experiments over the last century have found extremely tight constraints on violations of Lorentz symmetry, so any theory that reintroduces a preferred frame must hide it at accessible scales or produce effects below current detection thresholds. Some presentist-leaning philosophers insist that a metaphysical now need not correspond to a detectable physical structure, but scientists usually prefer explanations that have potential empirical impact. In short, presentism is not ruled out a priori, but it's less natural given the empirical triumphs of relativity. On the other side, advocates of an emergent time picture often stress how robust the arrow and the sense of flow are at the macroscopic level, even if time is not fundamental. Decoherence, the process by which quantum superpositions become effectively classical due to interactions with their environment, explains why macroscopic systems behave classically and why records are robust. Decoherence is not collapse. It's a predictable spreading of phase information into the environment that makes different branches effectively non-interfering. That process is deeply asymmetric in practice because it typically involves many degrees of freedom and an effective loss of phase coherence. Coupled with low-entropy initial conditions, decoherence helps explain why histories look definite and why we have a strong asymmetry between past and future in practice. Finally, there are concrete experimental horizons to watch. Measurements of the cosmic microwave background and searches for primordial gravitational waves continue to probe the earliest moments of the universe, and thereby test ideas about initial low-entropy conditions. Black hole observations, imaging horizons, measuring gravitational waves from mergers, searching for echoes or deviations from classical predictions, offer a window into strong gravity, quantum regime phenomena. Laboratory tests pushing quantum mechanics to larger scales will probe whether objective collapse or gravity-induced decoherence has any role. Proposed experiments to check gravitationally mediated entanglement could show whether gravity is a quantum channel. And more speculative probes, like precise tests of Lorentz invariance or searches for tiny violations of unitarity, might one day constrain or support exotic modifications to time's role. All of this keeps the question, is time an illusion, usefully alive? The question isn't a single cliff you either fall off or safely cross. It's a web of related inquiries. Which aspects of time are emergent? Which are fundamental? How do information and geometry relate? And how do our cognitive faculties produce the vivid perspective we call the present? Physics has given us tools to translate those philosophical questions into equations and experiments, and it has shifted the landscape away from naive intuitions and toward a richer, layered view. That layered view lets you be a realist about many things. You can accept that spacetime has a robust geometric structure that makes eternalism a natural account at a certain level, while also recognizing that the passage of time, memory, anticipation, and agency are real phenomena that arise from thermodynamics, information flow, and brain processes. So as research continues, keep an eye on the interplay between theory and experiment. Each new constraint on collapse models, each push to create larger quantum superpositions, each black hole observation, and each cosmological measurement nudges the philosophical options. The answers we're after are not merely metaphysical luxury. They are the consequences of how the universe arranges information and how that arrangement allows, or forbids, the processes we rely on to make decisions, write records, and remember. The debate about time is far from settled, but it's becoming increasingly concrete, and that makes it an exciting place to watch science unfold. We've already seen how physics pulls us toward a layered picture. At the deepest mathematical level, time might be something very different from the picture painted by everyday experience. At biological and social scales, the arrow and the flow of time are vivid and indispensable. Let's now unpack some of the key mechanisms that make the flow feel so compelling, show how modern information theory and thermodynamics tie into the story, and follow the thread through experiments and thought experiments that test the limits of our intuitions. Start with a deceptively simple point. Information is physical. That sounds like a slogan, but it has concrete consequences. When we say our memories make the past feel fixed, we mean there are physical records, synaptic changes in the brain, ink on a page, magnetized regions on a hard drive that correlate with past events. Writing down a fact, creating a stable memory trace, or erasing data all require physical processes that use energy and produce heat. Landwehr's principle, a foundational result from the physics of information, tells us that erasing one bit of information has a minimum thermodynamic cost. A certain amount of energy must be dissipated as heat. This links information processing directly to entropy increase. So the act of recording the past, making traces that persist, is thermodynamically asymmetric. You generally expend energy and increase overall entropy to create durable records. That asymmetry helps explain why we have reliable traces of what happened earlier and not reliable traces of what will happen later. Maxwell's demon is a classic thought experiment that pushes on this connection. Imagine a tiny being that can sort fast-moving and slow-moving gas molecules, letting through only the fast ones to one side of a box and the slow ones to the other, apparently decreasing entropy without doing work, violating the second law. For a long time, this seemed like a paradox. The resolution, worked out in the 20th century by people like Leon Brillouin and later by Rolf Landwehr and Charles Bennett, shows that the demon's information processing, measuring molecules, storing results, and erasing memory carries a thermodynamic price. When you account for the cost of resetting the demon's memory, entropy overall increases. The moral here is important. The arrow of time is intimately tied to how information is acquired, stored, and erased. You can't cheat the thermodynamic bookkeeping by clever bookkeeping alone. This connection between information and thermodynamics also clarifies why the flow of time feels like a stream of causes making effects. In many processes, information about earlier states is carried forward in the form of correlations and records. Those records allow us to make reliable inferences about the past, and because the act of creating them increases entropy, the direction from lower to higher entropy becomes the direction in which records accumulate. If you imagine a hypothetical world without such an entropy gradient, you wouldn't find durable records piling up toward one direction, and the difference between past and future would be much less obvious to embedded beings. Another illuminating idea is coarse graining. At microscopic scales, every particle has a position and momentum, and the fundamental laws can, in many contexts, be written in a time-symmetric way. But we don't keep track of every microscopic detail. Instead, we describe systems using macroscopic variables, temperature, pressure, density, which average over vast numbers of microstates. That averaging, or coarse graining, is where statistical irreversibility shows up. When you only record coarse-grained information, many microstates correspond to the same macrostate. Statistically speaking, you're overwhelmingly likely to move from macrostates that correspond to few microstates to macrostates that correspond to many microstates. That's the statistical root of entropy increase. The key point: the apparent flowing direction of time is emergent when you consider coarse-grained descriptions, and the fact that the universe started in a very special low-entropy configuration. Now let's circle back to a technical but practically important distinction: proper time versus coordinate time. In relativity, proper time is the time measured by a clock along a given world line. It's what your wristwatch reads as you go about your life. Coordinate time is a label that a particular choice of coordinates assigns to spacetime. Different observers use different coordinate systems. Operationally, proper time is what you measure, and it's invariant for a given path through spacetime. That's why astronauts returning from high-speed trips have experienced less proper time than people on Earth. Clocks in motion or deeper in gravitational wells tick differently. The manifold of spacetime doesn't come packaged with a single privileged coordinate time that everyone must use. But we can and do pick convenient coordinate systems for descriptions, like cosmic time in cosmology. These operational distinctions help explain how the block picture and the experience of passage can peacefully coexist. The block contains all proper times laid out, while your experience runs along your particular worldline in proper time. Quantum mechanics adds a second layer of technical subtlety around time. Unlike position or energy, time in quantum theory usually appears as a parameter, not as an operator in the same way. Pauli argued that there's no self-adjoint time operator conjugate to a Hamiltonian with a bounded spectrum, in the same way position and momentum are conjugates, which complicates a naive attempt to treat time on equal footing with other quantum observables. Practically, this doesn't block treating time operationally, by taking other degrees of freedom as clocks and describing correlations, but it does point toward the broader conceptual move many researchers are making. Treat time relationally. That is, ask how one part of a system changes relative to another part chosen as a clock. This relational approach is not just abstract philosophical gymnastics. It's an active strategy in quantum gravity research where there is no external time parameter to lean on. Speaking of quantum gravity, remember how black holes forced a rethink of entropy and information. In the 1970s, Jacob Bekenstein and Stephen Hawking discovered that black holes have an entropy proportional to the area of their event horizons and a temperature-emitting Hawking radiation. That forced physics to take seriously the idea that spacetime geometry can possess thermodynamic properties. More recently, calculations that combine semi-classical gravity with ideas from quantum information, entanglement entropy, quantum extremal surfaces, and replica trick techniques, have produced the page curve for an evaporating black hole, suggesting information isn't destroyed after all. Those developments show that information, geometry, and thermodynamics are deeply entwined, and they hint that any lasting explanation of time's arrow will have to reckon with how geometry stores and processes information. Now consider a line of experiments trying to probe the interface between gravity and quantum mechanics in the lab. If you can place increasingly large masses into quantum superpositions and observe interference, you're showing that quantum behavior persists far from the microscopic scale. On the other hand, if superpositions break down in a way that can't be explained by environmental decoherence, that could signal an objective collapse mechanism or a novel gravitational decoherence effect. People have been pushing matter-wave interferometry to heavier and heavier molecules, and optomechanics experiments aim to put tiny mirrors and mechanical oscillators into quantum states. Another proposed test, recently gaining traction, is whether gravity can mediate entanglement. Put two masses in spatial superposition and let them interact only via their gravitational field. If they become entangled, that would suggest gravity itself must have quantum properties. The protocols by Salgado Bose, Chiara Marletto, Vlatko Vedral, and others lay out how such tabletop experiments, while extraordinarily challenging, could one day probe whether gravity behaves classically or quantum mechanically. The stakes are high because the answer influences whether time and spacetime might be fundamentally quantum entities or emergent classical ones at large scales. Let's pause and connect these technical strands back to the human scale, where questions about responsibility, choice, and meaning live. Suppose we take the block universe seriously. Past, present, and future are all laid out in four-dimensional geometry. Does that make our choices meaningless? Not necessarily. The kind of agency we value, the capacity to reason, weigh options, respond to reasons, is realized by physical processes in the brain and body, embedded in spacetime. Even if those processes are located in the block, they have causal powers. Changing how you think now changes what later events will be like. From a decision-theoretic standpoint, uncertainty about future outcomes remains real. Whether the uncertainty is due to ignorance of initial conditions or to quantum indeterminacy, it still shapes our deliberation and planning. In that sense, practical freedom, the ability to act according to reasons and respond to incentives, is compatible with a block description. Many philosophers call that compatibilism. Moral responsibility and rational agency don't require a metaphysically open future. They require proper causal grounding and psychological capacity. If instead you're seeking a metaphysical engine of genuine openness, a fundamental process that turns future possibilities into present facts, quantum indeterminism via collapse seems attractive. Objective collapse models like GRW, Ghirardi-Rimini-Weber, or continuous spontaneous localization, CSL, posit extra dynamics that cause wave functions to localize stochastically over time, making measurement outcomes truly random in a single history. Those models restore a form of becoming. The wave function objectively reduces, and definite events arise out of quantum spread. But they come with trade-offs. They modify standard quantum mechanics, predict small deviations that experiments could detect, and must be tuned to avoid conflict with known phenomena. So far, the mainstream quantum theory has held up well, but the search continues. If a genuine collapse mechanism were discovered, it would give a strong physical basis for a kind of ontological openness, but it wouldn't by itself solve every philosophical worry. Randomness is not the same as agency. Another frequent worry is the potential for paradoxes if information could be sent backward in time. Many thought experiments imagine devices that send messages into the past and then produce logical contradictions. What physics teaches us is that causal structure, light cones in relativity and quantum field theory's microcausality, sets strict limits on what can influence what. Exotic solutions that allow closed time-like curves, paths in spacetime that loop back to earlier times, exist mathematically in general relativity, but they create paradoxes like the grandfather paradox. Most physicists suspect such solutions are either unphysical or prevented by deeper principles. For instance, some expect quantum gravity effects or energy conditions to rule them out. There are theoretical safeguards too. Consistency conditions like the Novikov self-consistency principle propose that only self-consistent histories can occur, preventing contradictions in closed-loop scenarios. These ideas are speculative, but they underline an important point. The universe's causal architecture is delicate, and our inability to easily access or manipulate future events is central to its stability. On the level of lived experience, neuroscience sheds light on how the mind constructs a coherent temporal narrative. The brain integrates sensory inputs over short time windows, combines them with memory, and uses predictive models to anticipate what will happen next. The resulting subjective now is sometimes called the specious present, the idea that the present moment as experienced has a non-zero duration, a temporal grain in which events are bound together into a unified perception. Experiments on temporal binding show that the brain can resolve sequences down to tens of milliseconds and integrate information into a continuous stream. Predictive coding frameworks suggest the brain is constantly minimizing prediction error by updating models based on incoming data. That inherently temporal process gives rise to the feeling of being carried forward through events. So the vividness of now and the felt flow are not mystical. They're the output of active, temporally extended neural processing tuned by evolution to support survival and planning. Memory is also instructive in another way. It's reconstructive. When you remember, your brain doesn't replay a faithful internal movie. It pieces together traces, filling gaps and integrating context. This reconstructive nature explains why memories can be distorted and why eyewitness testimony is fallible. But it also links to time's arrow. Reconstructing and stabilizing memories requires energy, and the resulting records are part of why we experience the past as fixed. The asymmetry between remembering the past and anticipating the future is rooted in these thermodynamic and informational constraints. You can build records of inputs received, but you can't build records of future inputs without a causal pathway conveying that information to you ahead of time. Let's examine a few thought experiments that illuminate these ideas more vividly. First, imagine an idealized scientist who could perfectly measure the microstate of the universe at one instant, every particle's position and momentum. With a perfect deterministic theory and infinite computational power, she could in principle compute both the past and the future uniquely. That sounds like a world where the future is fixed and knowable. Two problems arise. One, it's practically impossible to measure the entire microstate with arbitrary precision because of quantum uncertainty, and because any measuring device would need to be coupled to the system, altering it. Two, even classically, there's the issue of sensitivity to initial conditions. Chaotic dynamics amplify tiny measurement errors into huge differences later on, rendering long-term prediction meaningless in practice. So even in a deterministic block, epistemic limitations, what we can know and compute, create a real kind of openness in our lives. We act under uncertainty, plan under risk, and make choices that have meaningful consequences given our information. That practical indeterminacy is what matters for everyday life. Another classic thought experiment is the time traveler who brings a reliable news report of the future back to the present. If you could read tomorrow's winning lottery numbers today, your world would change. You could make different bets and alter the course of events. But physics makes such simple causal loops extremely hard because producing that report would require a mechanism to send information backward in causal order. The only ways out are either a consistent causal loop, where the report is part of the chain that leads to its own creation, which invites paradoxes, or prearranged correlations that look like future information, but were actually set up earlier. In realist terms, a future report being in the block does not mean it is accessible now. Causal constraints govern what can be known and when. We can also press on philosophical distinctions. Presentism insists only the present exists. Eternalism says all times equally exist. Growing block theory occupies a middle ground where the past and present exist, but the future does not yet. Each view faces different challenges when confronted with physics. Relativity seems uncomfortable with presentism because of the relativity of simultaneity. There is no invariant way to identify a single global present across all observers. Growing block theory can sometimes be made to work with a relativistic account if one takes a local notion of becoming rather than a global one, or if one's growth dynamics respect Lorentz invariance in some way. Eternalism fits smoothly with relativity, but then has to explain why we have such a strong sense of flow. These options illustrate that philosophical positions about time cannot be decided purely by intuition. They must be weighed against empirical constraints and conceptual coherence. Another question that often comes up: if time is emergent, does that make physical laws that use time merely approximate? The answer is subtle. Emergence in physics doesn't mean false. It means that higher-level descriptions are valid and powerful within their domains. Temperature isn't a fundamental quantum operator, but thermodynamics reliably describes thermal systems at macroscopic scales. Similarly, if time or spacetime emerges from microscopic quantum degrees of freedom, then our usual physical laws that use time remain excellent effective descriptions at scales where spacetime is smooth. They might break down near the Planck scale or inside black holes, where the quantum structure of spacetime becomes important. Emergence therefore preserves explanatory and predictive power while pointing us to deeper layers where those descriptions need revising. Let's take a more concrete experimental look ahead. If someone succeeds in creating entanglement mediated only by gravity, that would be a remarkable signal that gravity has quantum degrees of freedom. That in turn would make frameworks where spacetime is itself emergent from quantum data more plausible. Conversely, if careful experiments find deviations from quantum theory that point to spontaneous collapse, tiny heating of matter, suppression of interference at particular scales, then objective collapse models will gain traction. Both outcomes reshape how we think about temporal ontology. A quantum gravity that yields a timeless Wheeler-DeWitt-like equation, but from which time emerges relationally, would push toward a block-like effective description that's nevertheless grounded in quantum correlations. Either way, the story is moving from abstract metaphysical debate toward empirical constraints. It's worth spending a moment on the cultural side, how these scientific pictures affect how people talk and feel about time. Popular presentations often frame the block universe as everything is already written, which can sound fatalistic. That emotional reaction is understandable, but it's also a misreading. Being located at a particular point in a four-dimensional structure doesn't negate the reality of deliberation, the meaningfulness of choices, or the ability to change your environment in ways that matter to later events. The operational reality that your decisions have causal impacts and that uncertainty shapes your planning remains robust. In practice, people's lives run on timescales and causal patterns where reasons, incentives, and feedback loops do their work. Scientific metaphysics rarely cancels the ordinary significance of moral responsibility or personal projects. To make this concrete, consider planning a career. You choose to study, apply for jobs, network, and accept offers. Those actions alter your future experiences and the lives of others. Whether the timeline of your life sits in a block or unfolds as a presentist might imagine, the causal link between your choices and later outcomes is real and subject to feedback. The block picture simply represents those choices as part of a larger four-dimensional structure. From the inside, your planning and agency are lived realities, not illusions. Finally, and this is not a conclusion, just another thread to pull, there is still much to learn about how different arrows of time interact. The thermodynamic arrow, the cosmological expansion, the directionality of causation as enforced by light cones, and even arrows linked to quantum measurement and computational complexity often point in the same direction in the physical world we inhabit. Why they line up so neatly is itself an explanatory challenge. Some proposals tie the alignment to boundary conditions in the early universe. Others explore whether deep information-theoretic principles enforce such alignment. Understanding that concordance is an ongoing area of research because it touches on the foundations of statistical mechanics, cosmology, and quantum gravity all at once. So far, we've threaded microscopic physics, information, thermodynamics, neuroscience, and philosophy into a single story about why time appears to flow and what that implies about reality. There are still corners left to probe. Precise models that implement objective becoming without violating relativity, the full quantum description of evaporating black holes, laboratory tests of gravitationally mediated entanglement, and the ultimate explanation of the universe's low-entropy origin. Each of these areas offers concrete experimental or theoretical targets, and progress in any of them will sharpen which metaphysical picture of time is most natural. One last technical point worth highlighting before moving on. The notion of entropy itself can be subtle. We often use entropy interchangeably with disorder, but more precisely, it counts the number of microstates consistent with a given macrostate or measures the information needed to specify the microstate. When gravitational degrees of freedom are involved, counting microstates gets tricky. For black holes, it points to the number of quantum gravity microconfigurations that give rise to a particular horizon area. That's why progress in quantum gravity often looks like progress in understanding entropy. If you can count microstates for a black hole, you're learning something about how spacetime geometry relates to quantum information. Those lessons feed back into the arrow of time question, because if geometry and information are two sides of one coin, then the growth of certain geometric quantities might provide new ways to think about arrows of time that are more fundamental than naive thermodynamic counting. As we keep pulling at these threads, something practical emerges. Time is a many-layered phenomenon. At the bottom, whatever the fundamental ontology turns out to be, there might be no classical flowing present. At the level of physics that governs galaxies, planets, and clocks, spacetime provides an elegant geometric arena that makes eternalist pictures natural. At the level of complex systems, brains, societies, legal systems, time's arrow and the sense of flow are real and indispensable, grounded in thermodynamics and information processing. The ongoing research programs in quantum foundations, black hole physics, and quantum gravity are not simply academic. They aim to reveal which of these layers is fundamental and which are emergent, and to show how the levels relate. So where do we go from here? There are concrete paths to follow. Experimental pushes to larger quantum superpositions and gravitational entanglement tests, astrophysical and cosmological observations that probe the universe's early conditions and black hole behavior, and theoretical programs that attempt to derive time from quantum or informational primitives. Each step promises to convert philosophical options into empirical questions, and that makes the next few decades especially exciting for anyone interested in time. Each of those research fronts, tabletop quantum gravity probes, collapse model tests, black hole thermodynamics, cosmological observations, point in the same practical direction. The metaphysical options about time are narrowing into testable scientific programs. But what does that narrowing mean for the way we think, plan, argue, and live? It helps to translate these abstract debates into a few concrete domains where the differences matter and where the science forces us to sharpen our language. First, consider forecasting and prediction. Whether models, economic models, pandemic projections, these are all about predicting future states based on available data and causal models. Whether the universe is a block or something that comes into being doesn't change the fundamental nature of prediction. Forecasts are conditional claims about how systems will evolve under stated assumptions. What physics adds is a better appreciation of the limits of prediction. Determinism, chaos, quantum uncertainty, and practical limits on measurement mean that our forecasts will often be probabilistic. The important point for everyday life is that unpredictability doesn't imply metaphysical openness in some grand sense. It just means we lack information or the computational power to turn the governing laws into exact outcomes. So when you check a weather forecast and it says 70% chance of rain, that probability is a real operational guide for action. It reflects epistemic uncertainty and model-based risk, which is the kind of uncertainty that matters for decisions, insurance, and public policy. Second, in ethics and responsibility, some people worry that physics undercuts moral responsibility. If future events already exist in a four-dimensional block, are we still blameworthy or praiseworthy? The short answer is yes, at least from a practical standpoint. Legal systems, moral psychology, and interpersonal ethics all operate at a level where actions have causal consequences and where agents respond to reasons. Those causal relations and normative practices are embedded in physical processes, brains making choices, institutions shaping incentives, social feedback reinforcing norms. Whether those processes inhabit a block diagram or a becoming stream, they can still be causally efficacious and meaningfully responsive to reasons. From the viewpoint of social practice, the relevant facts are about control and responsiveness, not metaphysical preexistence. Put simply, the laws of physics don't abolish responsibility, they explain the basis on which reasons operate. Third, in personal life, the block universe can be disconcerting in theory but practically neutral. The sense that my life is unfolding is grounded in memory formation, planning, and the thermodynamic asymmetry that lets us write durable records. Those are embodied processes. Even if all your moments are points in a four-dimensional manifold, your experience is tethered to a particular world line, to your body and brain moving through events. That tether constrains what you can change and what you can predict. So practical advice doesn't change. Set goals, form plans, take actions that alter likely futures. The fact that future outcomes are in some sense located in the same spacetime geometry as your present choices does not remove your ability to influence what happens later. Fourth, in technology and design, the physics of time is already being put to work. GPS engineers and astronomers routinely correct for relativistic time dilation. Precision timekeeping, atomic clocks, time transfer and synchronization networks relies on an operational understanding of proper time and coordinate time. As quantum technologies mature, devices like quantum clocks and entanglement-based time standards may shift how we measure and use time in communication, navigation, and synchronization. If gravity is ultimately shown to be quantum, that could change how we think about timing in gravitational wave detectors or near-extreme objects. For engineers, time is a resource to measure, allocate, and control. Whether the deeper ontology favors a block or a flow isn't as relevant as the practical methods that let systems interoperate reliably. Fifth, education and public understanding benefit from nuance. Popular headlines sometimes treat the block universe as a fatalistic thesis. All times already exist, free will is an illusion. That framing does a disservice to the complexity of the debate and to the practical realities of human life. A better public explanation stresses layers. Physics describes spacetime geometry beautifully at a certain scale. Thermodynamics and brain processes explain the felt passage of time. Quantum mechanics complicates matters further. And a complete understanding probably mixes geometry, information, and emergence. Teaching time this way helps people appreciate why the topic is philosophically deep without making it a recipe for nihilism. It's useful to return to a handful of concrete experiments and near-term empirical prospects because they sharpen how our metaphysical choices could change. One of the most talked about proposals is the gravitationally mediated entanglement test. The idea is to prepare two tiny masses in quantum superpositions and let them interact only through gravity. If after some interaction time, the masses become entangled, then gravity must be capable of transmitting quantum information, a strong hint that gravity itself is fundamentally quantum. If instead no entanglement is observed where standard quantum theory predicts it, that would signal new physics. Perhaps gravity induces decoherence or collapse. Either outcome forces a reinterpretation of how spacetime and quantum degrees of freedom cohabit and will have knock-on effects on how we conceive of time at the deepest levels. Similarly, interferometry experiments with progressively larger molecules and mechanical oscillators are pushing the boundary where classicality emerges. If these experiments keep finding coherent superpositions at ever larger mass scales, that supports the universality of quantum mechanics and suggests that any collapse-like mechanism, if it exists, must operate at scales beyond those tested. If deviations appear, then we'll have empirical support for dynamical collapse theories that provide a physical arrow of becoming. In both cases, the experimental results are directly informative about the metaphysical stories we can tell about time. Whether openness is a genuine physical process, or whether apparent openness is an emergent phenomenon built on deeper, deterministic, or at least unitary laws. Black hole observations are another frontier. Imaging horizons, measuring gravitational waves from mergers, and digging into the late stages of black hole evaporation are not merely exotic astrophysics. They are laboratories for the interplay of geometry, entropy, and information. The progress in calculating page curves and the emergence of island-like prescriptions suggest that our crude classical idea of a black hole as an information sink was too simple. If these quantum-corrected pictures continue to be validated and expanded, they could show how information and causal structure conspire to keep the universe consistent, and they might reveal new features of temporal ordering in highly curved spacetimes. Cosmology matters too. Better measurements of the cosmic microwave background, surveys of large-scale structure, and searches for primordial gravitational waves help constrain models of the early universe. These constraints feed directly into hypotheses about why the early universe had such low entropy and how arrows of time arose. If we find evidence for a particular kind of inflationary model, or for a bouncing universe, or for some other mechanism, those data will shape the plausibility of different explanations for the thermodynamic arrow. The appeal of a past hypothesis, that the universe began in a special low-entropy state, is strong. The scientific task is to explain why that boundary condition obtains. As observations sharpen, philosophical speculations sharpen into testable claims. Another set of experiments focuses on decoherence and the thermodynamics of information. Advances in quantum thermodynamics, exploring heat, work, and entropy at microscopic scales, reveal how information processing costs manifest in tiny systems. These studies make Landor's principle operational and probe how memory formation, erasure, and measurement truly cost energy. That's relevant for our account of why memory points backward. Forming records tends to increase entropy. In devices with extreme isolation and control, researchers can see the interplay of coherence and thermodynamic irreversibility in ways that push the metaphysics into empirical terrain. As we look at these experimental prospects, a useful mental habit is to keep questions concrete. Instead of asking, "Is time real?" which is ambiguous, ask, "At what scales is a geometric spacetime with a block-like ontology an accurate description? At what scales does an emergent thermodynamic arrow explain memory asymmetries? What experiments would show that the future is physically open in an ontologically robust way?" Scientists can turn each into an empirical program. That reframing converts a metaphysical dispute into a scientific research agenda. One persistent source of confusion is the temptation to equate indeterminism with freedom. Randomness by itself isn't meaningful agency. If quantum collapse injects randomness into the world, that doesn't automatically deliver control, reason's responsiveness, or moral responsibility. What libertarians about free will often want is that choices are not fully determined by past states, a metaphysical openness, but they also want those choices to be attributable to the agent. Pure randomness undermines attribution, because if choices were mere chance events, praising or blaming someone would seem misplaced. Compatibilists have long argued that freedom and responsibility are about the right kind of self-determination, acting according to desires and reasons, even if those desires arise from preceding causes. Physics doesn't settle this philosophical debate for everyone, but it does clarify that invoking quantum randomness is not a straightforward route to rescuing a notion of free will that requires both indeterminacy and agency. A different conceptual knot is the issue of temporal experience. Why do we feel time passing if the block picture is adequate at the physical level? Neuroscience offers an answer that's both less mystical and deeply informative. Our brains are prediction and record-making machines that operate under energy constraints, and that use past information to build models that help control the future. The act of prediction itself stitches together sensations into the continuous feeling we call now. That feeling is very real, but it is a phenomenon produced by particular physical processes, not evidence for a metaphysical conveyor belt of moments. Accepting that doesn't belittle the lived experience. It explains it in terms that can be empirically studied and manipulated. A recurring metaphor in this debate is the film strip or the road map. Both convey useful but limited images. The film strip emphasizes that all frames can be stored and that running the projector creates the experience of motion. The road map emphasizes that locations exist and that moving along the map corresponds to visiting different points. These metaphors can mislead if taken too literally. The physics suggests a more nuanced picture. At certain levels of description, a block-like geometry is the most accurate representation. At other levels, thermodynamic, biological, dynamic, processual descriptions are indispensable. Good metaphors highlight one layer without pretending to be fundamental. This layered view has practical consequences for how to think about agency, planning, and responsibility. If you accept that what matters most for these domains is causal efficacy and information flow, then the metaphysics of time becomes less threatening. You can take seriously the physics lesson that simultaneity is relative and that the global present is not singled out, while also being confident that your choices have real causal consequences within your local light cone. The world doesn't become apathetic, it simply reveals its structure at different scales. Before wrapping up, it's worth addressing a few widespread misconceptions that the science sometimes fuels. Misconception. If the block universe is correct, then the future is already fixed and you can't do anything to change it. Reality. In a block universe, actions are still causes that make a difference to later events. The block simply represents those causal chains laid out in 4 dimensions. You cannot change what your past actions have already caused, of course, but you can influence future outcomes insofar as your choices are causally effective. The inability to change the past is not a metaphysical constraint unique to eternalism, it's a factual constraint of causality. Misconception. Quantum indeterminacy means you are not responsible for your actions. Reality. Randomness doesn't equal agency. If decisions were wholly random, responsibility would be hard to ground. Instead, philosophical and empirical approaches to agency emphasize reason's responsiveness, capacities for deliberation, and the causal role of intentions, things that can exist whether or not some micro-level processes are indeterminate. Misconception. Time being emergent means all our temporal experiences are illusions and therefore meaningless. Reality. Emergence doesn't imply falsity in practice. Temperature is emergent from microphysics, yet indispensable and real at the scale of weather and engineering. Similarly, the flow of time can be emergent and still be a genuine, causally potent phenomenon for organisms and societies. As experimental and theoretical work continues, the most interesting outcomes will be those that force us to revise how the layers fit together. If experiments show new physics, objective collapse, quantum gravity effects, novel decoherence channels, then our metaphysical story will shift. If not, the layered account, block-like geometry underlying emergent temporality grounded in thermodynamics and information, will gain more support. Either way, The progress will clarify which questions were empirical in the first place and which were philosophical. That's a healthy outcome. It means the debate is being translated into a program of testable hypotheses. So how should someone approach these ideas in their own life? You can keep three attitudes in balance. Be scientifically curious. These are active areas of research with real experiments on the horizon. If you enjoy the intellectual challenge, follow developments in quantum foundations, gravitational physics, and thermodynamics. They will change what seems plausible and why. Be practically engaged. Even if metaphysics unsettles you, remember that everyday decision-making, planning, moral responsibility, and scientific forecasting operate on temporal structures that remain robust under either philosophical picture. Continue to set goals, cultivate habits, and make plans based on likelihoods and reasons. Be philosophically nuanced. Recognize that questions like, "Is time an illusion?" are underdetermined by intuition alone. It's reasonable to accept that time is both a structural, geometric feature of the world at one level and an emergent, experiential reality at another. That pluralistic stance honors both physics and human experience. The debate over time is not an argument to be won once and for all by a single paper or experiment. It's a conversation between how we model the world, how the world actually behaves, and how living things like us experience and act within it. Over the coming decades, experiments will chip away at the choices, narrowing the space of plausible metaphysical interpretations. In the meantime, the philosophical side keeps asking for conceptual clarity. What do we mean by exists, flow, or now? While the empirical side keeps building experiments that translate those words into measurable consequences. To bring things back down to earth, when you set an alarm for tomorrow morning, that action is grounded in physical processes. You, your phone, the clock, and those processes are governed by the same physics that gives rise to debate about the block universe. The difference between the metaphysical pictures is unlikely to change how alarms work, how we remember mornings past, or how we plan for exams. But understanding the deeper story enriches our perspective. It reminds us that our sense of time is rooted in brains shaped by thermodynamic constraints, that clocks are devices sensitive to motion and gravity, and that the cosmos as a whole carries clues about why everything seems to point in one direction. In short, time is many things at once. At the level where physicists write equations for spacetime, a block-like, four-dimensional structure is a powerful and coherent description. At the level where thermodynamics and information processing matter, arrows and flows are real and explanatory. At the level of human life, memory, deliberation, and responsibility are robust features that make time feel like a sequence of becoming. The challenge and the beauty lies in understanding how these layers connect. That's where the next wave of experiments and the next round of philosophical work will be richest. As we refine our measures, sharpen our theories, and learn to translate metaphysical intuitions into testable proposals, the question, is time an illusion? Will stop being a rhetorical slogan and become a precise program of scientific and conceptual investigation. Until then, we can live and plan as if the future matters, because in practice it does, whether it's already on the map or being made as we move along.